This is page 23 of the synchronization notes. This is the last page, but it's a bit of a long one. So this is non-solution number 2 to the reader's writer's problem. It's getting closer to the solution, but not quite there yet. And the actual solution is part of the problem set 5. This solution here is also from the little book of semaphores that I told you about before by Downey. And the idea here was that a reader will let other readers into the room. So readers let other readers into the room. And the way this is going to work is we are going to have a room empty semaphore. Now, same name as before, but note that this is now a semaphore. There's a good reason for that, which I realized when I attempted to code it before, and hopefully you'll be able to see it before I tell you. This semaphore is initialized to 1. It's sort of acting like a mutex. Now, we do have a mutex. And of course, that's always initialized to 1. And it's used to protect access to the number of readers, or the readers count. So the readers count is initialized to 0. We have the pseudocode for the writer task and the pseudocode for the reader task. And the writer task is fairly straightforward, so let's do that first. I used green for the mutex. I'll do the same style here. So we're going to wait room empty. So if it's not empty, the writer will block. Then once the writer's in, the writer will do its writing, and once they're done, they will signal room empty to release it to let another task into the room. So the writer needs to keep, the readers need to keep track of how many readers are in the room. And the first reader into the room is going to wait on room empty, and the last reader to leave the room will signal room empty. So only the first in and last out will deal with room empty. So we need to acquire the mutex before increasing the reader count. So readers plus plus. And now we want to know if we're the first reader in the room. If the number of readers is currently 1 and we're it, then we know we're the first in the room. So if readers equals 1, then this task needs to acquire the room empty semaphore. So it's going to wait room empty. And eventually, either the room is empty and it will get it right away, or the writer that's in there will finish, will signal room empty, and then the reader will acquire it or unblock. So then it should release the mutex so that other readers can do their thing. And it is going to do the read. So this is, the before, and then we've got the read part. And then when it's done, what it's going to do is again acquire the mutex. And it will decrement readers. And now if it's the last one, the last reader in the room, it needs to make sure that it signals room empty so that the next either writer or reader that comes along will be able to enter the room. So if readers equals 0, then it should signal room empty, and it's done its thing, so then it should release the mutex. So that's the after writing part. So let's just say the second reader comes along. So the first reader went through the steps of waiting on room empty. So room empty is now 0. And so the second reader comes along before that first reader leaves the room. It'll increment readers after acquiring the mutex. So it'll see that readers is not 1, and it'll be 2. So it won't wait on room empty. So it's not the only one in the room. It will release the mutex. It will do its reading. You'll have any number of readers in there at one time. And when, let's just say, the second last reader leaves the room, they'll decrement readers. The number of readers will be 1. So they won't signal room empty. They won't say the room's empty. They'll just release the mutex. But the last one out will signal room empty. And that's basically it. Now, I said there was a reason that room empty had to be a semaphore. And the reason for that is here and here. So why does it need to be a semaphore? It looks like it's being used as a mutex. The reason is that the first reader that enters the room might not be the last reader to leave the room. So you might have different tasks signaling room empty than the one that waited on it. And a mutex will only let the owner release the mutex. So it has to be the same task if it's a mutex. If it's a semaphore, then it doesn't have to be the same task. And that is why. So I'll just add a note here. Different tasks might wait and signal, whereas only a mutex owner can release it. So let's look at how we're doing on the requirements. So which requirements have we met? So concurrent readers, exclusive writers, no starvation. So if you've been listening to me describe this, we are allowing multiple readers in the room at the same time. And if you look at this, you can see that only room empty will only be 1 once the last reader has left the room when it's empty. So if a writer waits on room empty and decrements it down to 0, it can be sure that it is the only task accessing the data. So we do have exclusive writers, but starvation is the issue here, and I don't know if you can see it, but the problem is that if you have a steady stream of readers arriving, they only the first reader will wait on room empty, and subsequent readers that come along will just have to acquire that mutex, bump up the readers count, and they enter the room. So as long as it never gets down to 0 readers, it will never signal room empty, which means that the poor writer on the left there will be stuck waiting at room empty forever. So a continuous stream of readers would not signal room empty, and a writer could block on room empty forever. Indefinitely is probably the better term to use there. So the solution to this is to basically see problem set 5, and what we do is add a turnstile, and the turnstile is used by the reader, so they will just wait it and then signal it right at the top. So up here they will wait the turnstile, signal the turnstile. The writer will wait this turnstile, but it's going to be a little slower about signaling it, which is going to make the readers pile up on the turnstile. So see problem set 5 for that one.